Hello, my name is Joseph Shin, and I'm a master's degree student in the Department of Applied Artificial Intelligence at Hanyang University Erica campus. Today, I'll be sharing our work titled Robust Eye Blink Detection Using Video Vision Transformer for the WCV 2024 conference. This is joint work with Jeongmin Hong, Juhee Choi, and Minsam Ko. The task that we are dealing with in this study is called eye blink detection. This is the process of locating the exact point in time a subject blinks their eye, enabling the acquisition of data such as blink rate or blink patterns in real time. Although the task may seem trivial, eye blink detection has been leveraged for a wide variety of applications such as detection of driver fatigue or students' attention and stress levels, diagnosis of ocular health conditions such as dry eye syndrome or computer vision syndrome, and even as a nonverbal communication channel for individuals with physical impairments. There are many approaches you can take to blink detection, some of which incorporate the use of sensors attached to the user's body or surroundings. Although these solutions are effective in many cases, our study focuses on RGB image-based eye blink detection instead, because we want to prioritize non-invasiveness and adaptability in different environments. Some conventional blink detection methods based on RGB imagery employ various image processing techniques such as motion vectors, image thresholding, and eye aspect ratio extraction. These approaches, however, tend to be more vulnerable to differences in conditional factors such as lighting or head movement. To surmount these inherent limitations, recent studies utilize deep learning architectures. Convolutional neural networks in particular have been widely used in binary classifiers that operate on single image inputs. Deep learning networks like these require image datasets with blink information for training and testing. A potential problem, however, is that the task is highly sensitive to environmental conditions such as lighting or camera angle. Most previous eye blink datasets being sampled from frontal view images of the subjects with similar lighting conditions do not account for this problem. An exception would be the HUST-LEBW dataset, which maximizes robustness by assembling images from movie scenes. Although immensely diverse in terms of conditional factors, the HUST-LEBW dataset lacks analysis of specific environmental components. The objective of this study is to develop a highly robust eye blink detection method, able to retain high accuracy in challenging conditions. To achieve this objective, we first newly proposed a dual embedding-based video vision transformer network for eye blink detection. To validate this approach, we also created the MAEB dataset by reflecting components of real-life situations. The proposed eye blink detection method starts out by sampling multiple sequential frames from the video for the input instead of single images. This allows the entire process of the eye's movement during a blink to be contained within the input. Afterwards, the eye region is cropped from the video frames using the YOLO V8 model, and the sequence is passed to the dual embedding module, which includes tubelet embedding and residual embedding. The embedding vectors are then processed by the transformer architecture, which classifies the input through the last MLP layer. We modified the conventional tubelet embedding from video vision transformers to include overlapping stride operations instead of the traditional patches. This allows capture of global contextual information, which is useful in situations where rapid movement is present in the image sequence, such as the subject moving their head around. Our proposed model also introduces a novel concept of residual embedding, which utilizes pixel subtraction between the original input and keyframe to leverage residual information. This enables capture of micro variations within the sequence, which is in turn useful when a blink sequence has clear pixel difference between the beginning, central, and end frames. This kind of difference is usually present when there is little to no head movement and the eyes are the only moving part of the image. As you may have noticed, the tubelet embedding and residual embedding both show effectiveness in opposite scenarios, allowing them to complement each other and create a more comprehensive model. To evaluate the robustness of the proposed DE-ViViT model, we first tested its performance under the in-the-wild conditions, meaning factors such as lighting and camera angle are immensely diverse. The proposed model was tested with a public HUST-LEBW dataset, along with its ablation study variants, a few baseline models, and also compared with results from other state-of-the-art blink detection models. Additionally, we explore the change in model performance with camera angle variation using our newly collected dataset called Multi-Angle Eye Blink, MAEB for short. This test was also conducted with the proposed model with its ablation study variants and the same baseline models. The two datasets used in this study can be briefly compared with a few characteristics. The HUST-LEBW dataset contains blink samples covering the entire blink process, with the frames being captured from movie scenes with unconstrained conditions. The MAEB dataset, on the other hand, although sharing the same structure of eye image data samples, focuses on variety of the camera angle aspect with other conditions kept relatively constant. In order to extensively explore the impact of camera angle variation, data from multiple camera angles was collected simultaneously for the same subject. In total, 1,440 image sequences were sampled from footage of 20 subjects from 9 different camera perspectives. A sample of this dataset can be seen on the right, where we can see image sequences of an eye blinking from 9 different perspectives. Now let's look at some results. 3 different architectures were selected as baseline models. The VGG16 network was modified for 10 frame sequences for the 3D CNN network, while a CNN LSTM architecture was trained with 2 different learning rates. A pyramid bottleneck network was also used, with 3 different block and branch variations. Ablation variants of the proposed model were used, the first being the original video vision transformer architecture, and the other being the video vision transformer with only tubelet embedding added. Looking at the results of the models being tested on the HUST-LEBW dataset, we can see that the proposed DE-ViViT model outperforms all other baseline and variant models overall. This can also be compared with results from state-of-the-art models being tested on the HUST-LEBW dataset in previous studies. Here, we can see that the DE-ViViT model has a higher F1 score than the highest performing state-of-the-art model in the comparison table. The models were also tested on the MAEB dataset sampled in this study, and the picture shows the performance of each model across the 9 different camera angles. From these results, we can see that all methods show performance drop in data from cameras located in corner areas, while the proposed DE-ViViT model shows the highest average accuracy with the most consistent performance with camera angle variation. Another aspect of the proposed model worth mentioning is the utilization of attention scores for precise blink timing. A question that may arise from the model input being a sequence of images instead of a single image is that it may lose the capability of pinpointing the exact frame in which the blink occurred. The proposed model, using the self-attention mechanism, is able to calculate the relative importance of each frame, which can be visualized as the displayed images. Here, the attention score shows peak value when the frame shows a closed eye, implying that this mechanism can be used in the future to refine the ability of the model to locate the frame of the blink. In conclusion, our work presents a dual embedding based ViViT for robust blink detection. We evaluated this model with the newly created MAEB dataset, which allowed extensive analysis of the camera variation aspect on blink detection. We envision that our insights can contribute to widening existing eye blink detection research fields and practical applications of eye signals. Thank you for listening. This is a presentation for the paper titled Robust Eye Blink Detection Using Dual Embedding Video Vision Transformer. Please feel free to contact me or the other authors if you have any questions.